I'm Mr. Laidan, and today we are going to have a final series of pharmaceutical calculations on the rate of flow of intravenous fluids, or rate of flow calculations. We need to know the secret behind intravenous fluids and how to go about them. We need to know the magic behind the flow of intravenous fluids. What determines exactly the rate of flow? What do we consider? The criticality of the patient will tell us whether we are going to run this IV fluid so fast, an average speed, or so slow. But how do we calculate this? How do we monitor the number of drops per minute? Let's have this equation here, which is a very interesting equation. So, infusion rate, the infusion rate, remember that rate means something over time. So infusion rate is calculated in terms of drops per minute. So drops per minute, this is the rate. And in order to calculate this, you need to have the certain volume of fluid which you need to administer to the patient. So we need to have the volume in terms of mils. Now, if you have your infusion, there is an infusion set just after the infusion. We know that there is a certain volume which goes through the infusion set or the giving set. So we need to multiply this volume by the volume of the whole fluid. So if we have the volume to be administered, then there is a certain volume passing through the administration set. Then this volume passes as drops per mil. So multiply by the infusion set, and this infusion set delivers volume in terms of drops per mil. Then you need to know for how long do you need to administer this intravenous infusion. Maybe that is dextrose infusion, normal saline infusion, lactated lingers, and whatever. So you need to know the time in terms of minutes. Having this, you shall have the rate of flow. So the flow, IV flow rate in terms of drops per minute is equivalent to volume in terms of mil, volume to be administered to the patient, times infusion set in terms of drops per mil, divided by time in minutes. But sometimes you may be calculating the infusion rate in mils per hour. Infusion rate in mils per hour. Then you need to have the amount of solution in mils, divided by the number of hours which you need to administer the fluid to the patient. Having known that, let's dig into some examples. A medication order calls for 100 mils of dextrose 5 in water to be administered over an 8-hour period using an IV administration set that delivers 10 drops per mil. How many drops per minute should be delivered to the patient? So when we counter words like how many drops per minute, that means you are looking for the rate of flow. So let's write the data here. So the medication order calls for what? For dextrose 5 in water. How much? This was so the volume of fluid. The volume of fluid is 100 mils. And this is dextrose 5 in water. This has to be administered over, so time, it was 8 hours. So, but it should be in minutes. Convert this to minutes. This is 480 minutes. Using an IV administration set, so the infusion set, the giving set to be used, it delivers 10 drops per mil. Delivers 10 drops per mil. So how many drops per minute? So what is needed is drops per minute, meaning rate of flow. should be delivered to the patient. So to know the flow rate, I said the flow rate in terms of drops per minute, you need to have the volume to be administered to the patient in terms of mils times the drip set, volume going through the drip set in terms of drops per mil, then you divide by time in terms of minutes. So having known that, what is the volume here? The volume is 100 mils. Then drops, the drip set delivers 10 drops per mil, and time is 480 minutes. So drops per minute, this is 100 times 10 divided by 480, that is 2.083. 2.083 drops per minute. So practically we have no 2 drops. So these are approximately equal to 3 drops per minute. Practically, as you are going to set this infusion, you are going to set it in such a way that the drip set, the giving set, will be dropping 3 drops per each minute. When 3 drops are dropped per each minute, this means after 480 minutes, the all 100 mils of infusion shall have been finished. Let's look at another example. Calculate the IV flow rate for 1,200 mils of normal saline to be infused in 6 hours. The infusion set is calibrated for a drop factor of 15 GTT per mil. GTT means drops per mil. So we are going to infuse 1,200 mils. These belong to normal saline, and time is 6 hours, equivalent to 360 minutes. Infusion set delivers 15 drops per mil. What is needed is the rate of flow. Okay, the rate of flow. How do we get the rate of flow in terms of drops per minute? We need to have the volume. This is 1,200 mils times the drip set. This is 15 drops per mil. Then time is 360 minutes. This will give us 1,200 times. This will give us 50 drops per minute. If these are 50 drops per minute, this means that we are going to set this drip set to deliver 50 drops each minute. If 50 drops are delivered in each minute, that means after 6 hours, 1,200 mils shall be finished and fully delivered to the patient. Let's go to the other concept of intravenous admixture, and this will be our last part. So admixtures are substances which are added into infusions to be delivered to the patient. For instance, drugs such as insulin, vitamins and minerals, antimalarials have the tendency to be put or to be added into infusions to be delivered into the patient because of several practical reasons. So due to that case, they are regarded as parenteral admixtures, meaning they are administered by any other route apart from the oral route. So when they are administered into such fluids, that's when we call them admixtures. So we need to know the principle behind the operation. What do we actually consider before we add them into infusions? So they should correlate to the dose of a specific patient. That's what we are going to learn. We are going to see how you can calculate the correct amount of admixture into the intravenous infusion. Let's check this example. Let's check this example. So a medication order for a patient weighing 154 lbs, meaning 154 pounds, calls for 0.25 milligrams of amphotericin B, this is an antifungal drug, per kilogram of body weight to be added to 500 ml of 5% dextrose injection. If amphotericin B is to be obtained from a constituted injection that contains 50 milligrams per 10 ml, how many milliliters should be added to the dextrose injection? So to know this question, to be able to solve it, you need to have information about the medication, information about the patient, and information about the fluid. Having known that, you will solve it in a simple and clear manner. Follow me. You are going to understand this in less than 2 minutes. So, our infusion, this is dextrose 5%. Then we shall have information about the patient and information about the substance to be added into the infusion, that is an admixture. Okay, so a medication call order for a patient weighing, so a patient weight is equivalent to 154 lb. When you change into kilograms, you divide by 2.2, that is probably 70. Okay, that is 70 kg for a patient. Calls for 0.25 milligrams of amphotericin B per kilogram of body weight. So the dose for this patient is 0.25 milligrams per kg of what? The admixture is amphotericin B. Okay, to be added. So this dose, after calculating the required amount of dose, should be added to the infusion, which is the volume of infusion is 500 ml of dextrose infusion. So if amphotericin B is to be obtained from a constituted injection, so available, we have a constituted injection of amphotericin B with the following strength: 50 milligrams per 10 ml. How many milliliters should be added? So we need to know amount in mils of amphotericin B to be added to dextrose, then delivered to the patient. First step, you need to know the total amount of drug to be consumed by the patient. Okay, the usual dose for this patient is 0.25 milligrams per kg, but this patient has got a total kg of 70 kilograms. If we multiply, you get 7 point, probably 0.25, that is 17.5. That is 17.5 milligrams. So this patient has to use 17 milligrams of amphotericin B. But how do we get 17.5 milligrams of amphotericin B? Is from this constituted injection which is available. So from this concentration of the injection, 50 milligrams are contained in 10 ml. Then 17.5 milligrams required are contained in how much mils? Then multiply by 10, divide by 50. This is 3.5 mils. Okay, the practical implication of this, how do we do it? We have got 3.5 mils of amphotericin B. So take a syringe, maybe a 5 cc syringe, then draw 3.5 mils. Draw 3.5 mils of amphotericin B from this injection and deliver it into this infusion, and thereafter run the infusion to the patient. Let's have two more examples, then we quit the session. This was an assignment in one of the classes. An intravenous infusion is to contain 15 milliequivalents of potassium ion and 20 milliequivalents of sodium ion in 500 ml of 5%. Using potassium chloride injection containing 6 grams per 30 ml and 0.9% sodium chloride injection, how many milliliters of each should be used to supply the required ions? So we have the infusion here. Probably this was dextrose 5% with the volume of 500 ml. But this infusion was to contain an admixture of the following: potassium, and sodium. These are the two admixtures which were to be added into this infusion. So how much of each? To contain 15 milliequivalents of potassium and 20 milliequivalents of sodium. Okay, so available drugs are in terms of injection. So the potassium chloride injection, we have the potassium chloride injection with a strength of 6 grams per 30 ml, and sodium chloride injection 0.9%. 0.9% meaning 0.9 grams in 100 ml. Okay, how many milliliters of each? We need to know amount of each in mils, which are to be considered as an admixture. How do we do this? We need to consider the concentrations given. The first concentration is about potassium chloride. So let's solve the amount of potassium chloride. So potassium chloride, the amount of potassium to be issued can be obtained from potassium chloride. So its concentration from the injection is 6 grams into 30 ml. Then how many milliequivalents are required? 15 MEq are contained in how many mils? So how do you do this? First, convert milliequivalents into grams. How do you do this? Remember, 1 milliequivalent of potassium chloride is provided by 74.5 milligrams. So 15 MEq are provided by how much? So this is 15 times 74.5. Then that is 1117.5 milligrams. Converting into grams divided by 1,000. Then that is 1.1175. Okay. Then put here 1.1175 grams, multiply by 30, divided by 6, that is 5.5 or 0.6 mils. Okay, to know amount of sodium to add. So sodium can be obtained from a sodium chloride injection with a concentration of 0.9 grams into 100 mils. Then 20 MEq can be obtained how? Then 20 MEq should be converted into grams. Remember that 1 MEq of sodium chloride is provided by 58.5 milligrams, and 20 MEq shall be provided by this. Okay, this is 58.5 times 20 MEq. Then this is 1170 milligrams. Obtaining grams divided by 1,000. If we divide it by 1,000, that is 1.17 grams. Okay, then substitute grams here. Substitute 1.17 grams. If you multiply by 100 divided by 0.9, you get 130 mils. So 130 ml of sodium will be drained from here, and 5.6 ml of potassium shall be drained and put into an infusion. The last example states that a person is to receive 2 milliequivalents of sodium chloride per kilogram of body weight. If the person weighs 32 lb, how many milliliters of a 0.9 sterile solution of sodium chloride should be administered? So this person, this is the dose now. This person was to receive 2 milliequivalents of sodium per kilogram. Okay, if the patient weighs 32 lb, weight of a patient, this is 32 lb, converting to kg, probably 14 point something, divided by 2.2, it is 14.54 kilograms. Then the available injection of sodium chloride is 0.9%. So first we need to know the total milliequivalents which is consumed by this patient. So 2 milliequivalents were to be consumed by a 1 kg person, but this person has got 14.54 kilograms. So how much milliequivalent should be taken by this patient? This is times 2, you get 29.09 milliequivalents. So these are the total milliequivalents to be consumed by this patient. So convert these into grams. Remember, this is sodium chloride. 1 milliequivalent of sodium chloride is provided by 58.5 milligrams. So 20 what? This is 29.09 MEQ of sodium will provide how many? So multiply by 58.5. This is 1701,818 MEQs. 1 MEQ 58. That okay. 58.5 times 29. Okay, those are milligrams. To obtain grams, divide by 1,000. Then that is 1.701 gram. Having known that, from the injection available, which is 0.9 in concentration of 100, so what about 1.701 gram? This will be found in how much? Then that is 189.08 mils. All right. That is all about intravenous admixture. You may have more practice questions. I'm Mr. Laidan from Spring Institute.